Well, thank you very much for having me. It's a pleasure to be here, and it's a pleasure to meet this group, that some of whom I've met before, and some of whom whose research I know quite well. So it's a pleasure to be here. Thank you for having me. I'll talk today about information processing and what I call political order. But let me begin with a question that I think many of you are likely familiar with. Where does one mind end and another mind begin? We've swung back and forth on this question. In the West, at least, in the intellectual tradition of the West, we've settled on primarily a single solution, something we call methodological individualism. And this is the idea that even for social phenomena, we have to reference our explanations of what we see solely to the beliefs and the desires and the thoughts of individuals. So in the case of economics, which is in some sense the most extreme example, at least as this tradition in practice, we have a reference individual, a single reference individual, who might interact with copies of himself, but in a sense he interacts with those copies as if they were strangers. So it's methodological. I'm giving perhaps an unfair treatment of how we've done things in the past. Of course, it's been quite successful. And we've been able to make many predictions, we've been able to explain many things, but of course, the idea that everything that happens in our lives can be referenced back to ourselves acting in isolation is something that, even in our personal experience, we know not to be entirely true. And so here's just one example. This is from the cartoonist Randall Munroe, who writes a comic called XKCD. I don't know if you guys read this here, but we're all sort of obsessed by it, so we all know it. One's experience of love, of romantic love and friendship is perhaps one of the examples where we like to think that the boundaries that are perhaps legally recognized by the state, for example, or by a doctor, the boundaries of our minds are somehow violated. So this is a great set of lines. You may have had this experience. I won't ask you if you've had with your first girlfriend or boyfriend, right? I like that song too. Like that pop song, you know, we're so connected. And in fact, actually, what's wonderful about this is, and I think Randall really gets this right? So this woman is saying, not that we're so similar. She's not impressed that we're so similar. She's impressed, in fact, that we're so connected. As we become adults, we realize that maybe we're not so connected and maybe we're just similar, and this is what's called homophily. And we all tend to practice homophily in our personal relationships. I don't know if you've noticed this. But when these two people say they feel so connected, I think one of the things that we're getting at is the idea that the thoughts we're having, the thoughts that these two people are having, are the way they are because they're aspects of a single underlying process, and that's what can be so exciting about love. So this is my brief history of group minds. This all, in the modern era, began in the 19th century, perhaps with somebody called Hegel, who I probably do not have to tell you about. But Hegel, in Phenomenology of Spirit, tells a story about history that is entirely cognitive. It's a psychological theory of history. And one of the reasons you know it's psychological is each chapter in the Phenomenology of Spirit, remarkably, has a third-person perspective on what's happening, and then actually provides, and that's why it's called phenomenology, actually provides a perspective of the historical process as if you were this single being experiencing the changing of consciousness over time, the revolutions in consciousness that happens. That's what, by the way, what makes it really hard to read. So skip to the third-person description of what's happening before you read the first person. I forget which order they're in, but one of them is far more confusing than the other. Of course, they're both profoundly confusing. So while we have personal experiences of this, and while certainly in the European tradition, the continental tradition, we have an understanding that we might be able to describe social systems as if they were cognitive systems. This is profoundly out of fashion in the United States. And you can't, in many cases, cannot even use the phrase group mind, social mind. These things get you in a lot of trouble. So I was talking a few years ago with a very well-known and fantastic researcher in cognitive science, and I used the phrase group mind. So, no, please don't use that term. It's okay, I won't tell anybody. So I had forgotten that I published a paper called Group Minds in the case of Wikipedia. But okay, so when in the Anglo-American tradition we try to talk seriously about the idea that the boundary of the mind is not just the boundary of the skull, there are two ways to do it. So I'll tell you the secret. There's two ways that they do it, or we do it. I give the first one this sort of junky phrase, propositionalism. It's just an informal way to talk about the idea that to have a thought, to think, To think is actually just to hold a set of propositions. And what is a proposition? Propositions usually are phrased in terms of sentences, right? So here are some propositions. If something or someone can hold these things to be true, things like this to be true, then that thing or that someone is also a mind, okay? And so I've given a sort of gradation here, and this is what we often think of as a gradation in the sophistication of the propositions you can hold, right? So it is raining. This idea that I'm holding the proposition that it's raining is something we think, for example, animals can do, even very unsophisticated animals. Now, why we think that, it's a whole different thing, but it's something that we imagine can be done by species other than ourselves. But as we go up in this hierarchy here, and so, for example, there's something quite different from declaring that it's raining and wondering about whether somebody else knows that it's raining or thinks that it's raining. These propositions, we make a distinction here. We call this the ability to attribute propositions to somebody else and have a proposition about somebody else's propositions, something we call theory of mind. And so there's this big question, for example, do animals have theory of mind? Can they recognize that something else might know something? And, we can create gradations within that. So, for example, it's one thing to know that, Evo knows that it's raining, or Evo thinks that it's raining. But let's say it's raining. Am I able to entertain the proposition that Evo doesn't think it's raining? So can I imagine other people not just having beliefs, but actually having beliefs that I believe to be false? We can talk not only about beliefs that other people hold, but we can also talk about what are called intentional states, goal-directed sentences, such as, I should take an umbrella. I should, wash my hands before eating. I should wear a bow tie. I should wear a suit. I should wear a t-shirt. Okay? Aspects of our social lives that include things like social norms. Okay? And finally, we can talk about this lovely phenomenon of what's called joint intentionality, which is where I have a goal-directed state, but in fact it's a goal-directed state that I share with others. Okay? So one example would be moving a couch together as opposed to picking up a chair. I usually need somebody to help me move a couch, and now all of a sudden it's not me moving a couch, but us together moving a couch. We'll talk a little bit more about that. So under this sort of theory of what it means to have a mind or to be a mind, okay, it's a theory about being able to entertain some set of these things. And this gradation here, we like to think of as sort of a set of naturalized categories. We like to think that these sentences really are distinctive in a way that corresponds to something that happens in the world. They're not simply philosophical distinctions, but they're things that actually might be represented as almost biological categories. So we debate a great deal, for example, as to whether or not animals can share or hold states that are joint intentional. There's a lot of debate that happens. So one question is, for example, can chimpanzees actually hunt together? Can they hold the joint intentional proposition that we together are hunting? Or is it, as Michael Tomasello says, and this is not a quote, but is it just sort of opportunistic chasing together? Okay? So whether or not the chimpanzee is able to do this, we think is almost a biological distinction. So even though these terms are things that philosophers have invented, we start to think, or at least under this theory of mind, or in this theory of what it means to have a mind, we make those distinctions, we think they're scientific, right? So propositionalism, it looks a little bit like we're never going to get mind beyond the skull, right? These are things, I can hold these sentences to be true or false. And maybe some of the animals can, but what would it mean for a group to hold these sentences true or false? And in fact, even though it doesn't seem this way, even though this seems perhaps like a rather old school sort of analytic philosophy way of talking, there is now a lovely tradition, or a lovely set of work being done, not just by John Searle, who we often attribute a lot of these sort of notions of intentionality and group intentionality to, but also, in fact, there's some lovely work by philosophers List and Pettit, who really have taken this to a much greater extent. So here's a way, for example, that we might use propositionalism to say that a group has a mind. We might want to say, for example, the group knows that X being some sense. The group knows that it's raining, okay? Or the group wants that X. The group wants to move the couch, right? And so, in fact, there is a way, or potentially a way, to translate or to show how individual thoughts, individual propositions, might together allow the group to hold a proposition that is in some sense beyond what the individuals themselves have. Okay, so what does it mean for the group to know that X? Well, perhaps, for example, for the group to know that X, it might be that not only does everybody know X, right? Not only does everybody think something, but in fact everybody knows that everybody else is thinking something. And of course, recursively down the line, not only does everybody know that everyone's thinking something, but they also know that everybody also thinks that. And so that infinite hierarchy is called the state of common knowledge. It's something we learned from a paper by Aumann called Interactive Epistemology. It was built originally for game theory, but this is a nice way to say, look, here's a whole bunch of individual mental states that might be both necessary and sufficient to attribute this group mental state to the system, okay? So there's another one, like the group wants to X, right? And so perhaps it's not only though that, each of us individually wants X to happen, okay? But we also perhaps, for example, know that everybody else wants this to happen and so forth down the line, okay? So this is a way that propositionalism allows us to get group level mental state. Has anybody coached like young kids playing soccer or seen young kids playing soccer? Football? Yes, okay, right? So you know what happens, right? Like the ball, like the entire team is all chasing the ball together, right? So they as of yet don't have the joint intentional state of being on a team, right? They all think they're individually in charge of chasing the ball. But once they're able to grasp the joint intentional state of being a part of a team, they realize that if the team wants to possess the ball, it doesn't mean that each individual has to go chase the ball. In fact, one of them can chase the ball and a couple others can go over there and take the pass, right? So this is a quite sophisticated thing, right? It's a little bit like the chimpanzees, right? Are all the chimpanzees chasing the monkey, or are they kind of spreading out in a way that actually helps somebody else perhaps get the monkey that then they might share? Okay? So having these states is not just having individual level states, it's having a certain set of individual level states that relate in a certain way, okay? So this is propositionalism. This is one way to give groups minds, okay? Here's another way, right? So instead of going to talk about sentences being held and certain configurations being held by individuals leading to certain group level propositional states, sentences that the group holds even though each individual doesn't necessarily hold them, we can go the other extreme and we can go to something that's called, well, I would give it the name computationalism, sometimes called functionalism. Okay? So if John Searle is the philosopher of Berkeley who's most associated with what I call propositionalism, the philosopher and the linguist most associated with computationalism is probably Noam Chomsky. Okay, although of course Noam Chomsky is not the person to invent functionalism. But he's somebody who came at a very different kind of problem, right? John Searle is interested in how small groups, political systems, people writing constitutions might lead to group level mental states. Chomsky's interested in a very different problem. Our language is clearly thoughtful. It's clearly a mental process. But when I form a sentence, at least when I form a sentence in English, I'm completely unaware. I have no propositional attitudes towards how I put my grammar together. I have to laboriously be taught that, and usually most of the sentences I produce have nothing to do with any kind of grammatical laws that Marta might have discovered at some point. The things that I do when I do language, they're clearly mental acts, but they're not mental acts that have any relationship to the kind of propositional knowledge that we're talking about. Chomsky, of course, takes this extremely far. He has this little universal grammar module that sits in the back of our head and is genetically coded in. Okay? Whether or not that's true, Chomsky realized that what you have to do if you want to understand the mental states behind language, okay, is to treat it as a computational process, as the output of some kind of underlying system that you understand mathematically. You don't understand it as a being holding a proposition, believing something, but rather you talk about the computational sophistication you need to describe that process. So there's something called the Chomsky hierarchy. I don't know who invented it. But it's a little bit like DEF CON, right? So the smaller the numbers go, right, the more crazy the language gets, the more sophisticated it gets. Okay? So you can describe certain very basic, what we call production rules, that can lead to certain languages, meaning certain sets of behaviors. And the more sophisticated the production rules, the most sophisticated and refined the behaviors can get, right? So we'll talk today quite a bit about what are called the regular grammars. Okay? These are descriptions of computations, allowable computations that are incredibly simple. There's a lot of things that regular grammars can't do. Just above them, in the Chomsky hierarchy, in the hierarchy of mental sophistication, okay, are what are called the context-free languages, and that actually corresponds to computer languages like Python. The way we describe what it means for a computer to compile some Python code or some C code or some Fortran code is for the computer to be able to do a computation, have a series of mental states, okay, that correspond to something that you require a context-free grammar to describe. So what a context-free grammar is, what that means, we won't get into it unless we can talk about it in the questions afterwards. So these are two really distinct ways to get at mind, okay? In one sense, mind is a set of propositions, and if they combine in certain ways, then groups can have minds. The other case, mind is attached to practically anything you like. Anything that produces a set, usually symbolic, but not necessarily behaviors, any kind of time stream, can in some sense be associated to a computational process. And to have a mind is simply to be a computational process. And this is something, perhaps it sounds weird if you put it that way, but of course this is underlying almost all of the AI that we talk about. Right? People want to build a little machine that sits in a room somewhere and has thoughts. Okay? That often, at least in the past, that has seemed totally natural to us. Right? That you can have a thinking machine as opposed to a thinking network of machines. So, while John Searle's idea of propositions, the way people, for example, in analytical behavior spend an enormous amount of time trying to split apart these intentional states, these levels, for example, of intentionality or levels of theory of mind. Okay? They spend a lot of time, even for something as similar to us and with as similar goals, let's say, as a chimpanzee. With the Chomsky approach, you could do it to anything. You do it to birdsong. You don't even have to know what the bird sounds like. Right? You could do it to some kind of alien message that comes down in the VLA. Right? You can listen to any kind of process and give it a computational description. Chomsky's original goal, which was to find the mental states corresponding, some hidden, inaccessible mental states corresponding to, say, English language grammar. Okay? Chomsky's original goal could be applied just as well to birdsong, and to say what's the grammar of birdsong, and therefore what is the mental states, what are the mental states that go inside that bird along with birdsong. So I think these two gentlemen and these two theories, propositionalism and computationalism, in some sense span the space of how we might talk about mind. Okay? Somewhere in between them, I think, is the thing we're most interested in, right? So, in a sense, Searle's ideas, the way Searle talks about what it means to have a mind is something that it's much easier for us to talk about when we're talking just about people and in particular small groups of people, right? It's the village, right? It's the nascent political order. It's the men, usually men, sitting around writing a constitution, okay? And what Searle is interested in a sense, is how groups can make those propositions legible to each other, how we can form groups where the mind of the group has some kind of relationship, some kind of legitimate relationship to the minds of the individuals. And on the other extreme, Chomsky's understanding of what it means to have a mind is so general that it's almost ahuman, right? Somewhere in the middle are kind of the statements like this, the statements we want to make, let's say about, and I've used the example of the market here for reasons that will become obvious in a second, the market believes that X, right? Now it's clear when we say that the market believes something, we don't quite mean that everybody in the market, every person participating in the market, for example, has common knowledge of X. In fact, most people don't. But at the same time, in attributing this kind of mental state to the system, we're doing a little bit more than Chomsky would. By attributing things like sentences, propositional sentences, we're pushing things a little further than computationalism allows us to. Okay? So what we'll spend a lot of time in this talk here, we won't really be able to do things that Searle does because the systems that we're talking about are so huge. And if they have group minds, if there are group level minds, there's certainly not these really high level, really stringent criteria that someone like Searle might demand of them. Okay? We can treat them as computational processes, but we can also try to get a little bit towards attributing mental states to them, almost as if they were people, or perhaps almost as if they were the sophisticated groups, the consensus-based groups, for example, that Searle talks about. So this middle I would call the self-organizing middle. Statements like the market believes in X, right? The market expects an X. I don't have a picture of them, but this is something that we get from Hayek in a fantastic paper that was written in the 1940s called The Use of Knowledge in Society. It's a beautiful paper. It's very short. I don't know how, people don't write this way anymore. But the way to get a sense of what this paper says is to ask a very simple question, okay? How much does it cost to make a pencil? So I ask my students this, right? Say you had to figure this out ahead of time, right? How much does it cost to make a pencil? And if you don't like the idea of using money, say, look, how much does it cost to make a pencil relative to how much it costs, I don't know, make a car or to harvest apples? How many apples do you need to give somebody in order to get a pencil out the other side? Okay? And so if you wanted to figure that out, a priori, if you wanted to actually calculate that on your laptop, you'd have to work out an enormous number of things that are fun to play the game, right? How much does it cost? Well, I don't know, do you have to mine graphite? Where does graphite come from? It's a little better than charcoal, right? I don't know where that comes from. Okay? You have some. Do you guys know where graphite comes from? No, right? No one knows, right? You guys don't know. I don't know, right? Okay. Like there's some factory where I guess they have to get the graphite and sort of press wood around it, right? Actually, side point, Thoreau, right? The American philosopher, he invented a way to do this. Okay, so labor conditions, right? Maybe as life gets better, or maybe life gets too hard, it's harder to get people to go make pencils for you, right? How do you get the pencils from whatever place they're making them, because it's probably not going to be here, to where you need them, where people need them, right? How much does it cost to pay somebody to pack the pencils into a box, and how much does it cost to get the longshoreman to load the box onto, right? There's an enormous amount of stuff that you would have to know to compute how much it costs to make a pencil. Okay? But then you go to Amazon, and Amazon knows. And how the hell does Amazon know it costs about 10 cents to make a pencil? Right? It's like magic, right? We don't realize how magic this is. But Amazon knows, and in fact, nobody who did this has any idea. Like, I'm sure if you asked, took a survey of the people at Amazon, and you said, how do they make pencils? They would have no idea. Okay? So if the market knows, it doesn't know in the way, for example, that Searle would like the market to know. Okay? The propositional states are much more distributed. Okay? And the reasons and the ways in which those propositional states are shared are much more complicated. They don't really correspond to the kind of legitimate organizations, or the organizations that are legible to us. These are not legible things. If it hasn't quite hit you how strange it is that I can just click a button and learn all of this crazy social science and economic science, I can just pull this up and learn that a pencil costs 10 cents. Right? If that doesn't strike you, right, well, imagine what would happen if you didn't have a market to do this. And of course, we did this experiment, and by we, I mean Homo sapiens did this experiment, and the Soviets did it. And under Khrushchev, they started realizing that if you were going to try to build a modern society, a globalized society that was trading and building and giving goods to, good comrades, and competing with the West in what kinds of consumer level products it could give, you actually had to figure out how to price a pencil. But if you were ideologically opposed, or for some reason unable to relinquish control to the extent you needed to relinquish control for this kind of magical system to work, what you had to do is you had to get a bunch of cyberneticists together to solve the problem, right? So they did this, actually. Khrushchev did this. I mean, things got bad after Khrushchev. He's like the nice guy of the Soviets, right? In some sense, he was not as crazy as Kennedy. So they actually did this, right? So they got all the academics, right, and they shipped them out to Siberia, which sounds bad, but it's actually not so bad, because they actually gave them a really nice life. It was like a big academic paradise, like the Santa Fe Institute, but bigger, right? And they had a lot of freedoms that the rest of the population didn't have. And the story is told in this book called Red Plenty, which is a really great read. Okay? And the thing was, they just couldn't solve the problem. Right? They couldn't solve the problem of how many Lagrange multipliers do you need to figure out every single factory in that country and everything it should be making, and exactly how to triangulate the limited resources you have to make sure everybody has pajamas and pencils in the right balance. They couldn't solve it. Now, the free market is not magic. It's good at pricing pencils. It's probably not so good at pricing houses, as we discovered. It was close, but it was probably off by a factor of 2 or 3 in 2008, and that's enough to crash everything, it turns out. Okay, it's not so great at pricing healthcare. At least in the States, it's not so great at pricing healthcare. So, we don't want to say this is magical, right? When the market is computing things, it's not simply computing economic facts, it's computing normative facts, moral facts as well. So, a lot of people don't want to admit that. It is. That's one thing we're trying to understand. Of course, the extent to which the market is also computing moral facts. We want to understand that, and if we're unable to talk about group minds, if we're unable to talk about the computations we do collectively, with distributed mental states, and there's, it's hard to think of something more distributed than the computation that gave you 10 cents from this Amazon page. Okay? When we're trying to do that kind of computation, we have to understand how it happens. Okay? So, therefore, mathematics, right? Boundaries of the mind. How do we understand distributed mental states? I'm going to give you a really simple example, and this is in one of our papers, a really simple example. We're going to take it very slowly, okay? But at the end, it's like the magic trick. Out the other side comes something you didn't expect, right? So everybody knows tit-for-tat. You learn it in the playground, and then you learn it again from Axelrod. So tit-for-tat, when you play the prisoner's dilemma, which I will not explain, so you should quickly Google prisoner's dilemma if you're, God, I hope you don't have to. But we're playing cooperate and defect with each other, right? There's this temptation to defect, right? I don't know if you feel it. I always play this game with collaborators before I collaborate with them, right? I say, we're going to play prisoner's dilemma, right? And you better hope they cooperate, right? Because if they think they're really smart and they defect against you, do you really want that collaborator? So tit-for-tat is a great way to play prisoner's dilemma, especially repeated prisoner's dilemma, right? And so I'm going to give you this little model. This is exactly the model that Chomsky would draw. Okay, this is a regular grammar, it turns out. okay, that describes the strategy tit for tat, okay? So these are the internal states of this person. In fact, we're going to call those the states of mind of this tit for tat guy. Tit for tat's pretty simple, okay? I have two mental states, cooperative, happy, and defected, okay, mad. And I'll just tell you that just, that if I'm a C, I'm just going to cooperate, right? And if I'm a D, okay, I'm going to defect. In this case here, my mental states correspond exactly to my actions, but if you're familiar with something called tit-for-tats, I actually now have three mental states. Two of them have the same behavior, but you can think of one as like annoyed and the other one as, sort of pleased. But tit-for-tat is even simpler, right? My mental states exactly correspond to my behaviors. Okay, then I have a decision rule, right? Which is that if I'm happy and someone cooperates with me, I stay happy. Right? If I'm happy and someone defects against me, right? Next time, screw you, excuse me, right? I'll defect against you. I'm mad, but if the person cooperates, then I gotta get pleased again, right? So this is just describing exactly how tit-for-tat works. Okay? So let's imagine a society of cooperators, okay? In fact, this is a very simple site, just two people, right? Alice and Bob. And Alice and Bob are both tit-for-tat players. They're identical copies. They have exactly the same logic and beliefs, but of course they can be in different mental states at different times. Now, if Alice and Bob are good tit-for-tat players, it's really boring because they cooperate all the time. It's a friendly strategy. They play C against each other, and they just play C forever. So in fact, you don't even notice, you don't even explore their mental state. So what we're going to do is we're going to add noise to their world. And occasionally what's going to happen is, Alice and Bob are playing lots of Cs. Occasionally, there's a lightning storm, and instead of one of the players playing C, as he or she intends, it plays a D. Okay? It's just a random flip with probability epsilon. Okay? So now what I'm going to do is build a little model, okay? And this is actually a model of the entire society. It has four states, okay? And these four states describe all the possible, what we call microphysics of their interactions, okay? So this state here is called the CC state. It's where Alice and Bob are both happy, right? They're both cooperative. Here's the DC state where Alice is mad and Bob is happy. Up here is the CD state where Alice is happy and Bob is mad. And down here is the DD state where they're both angry and they're both defecting against each other, okay? And what happens here is that we transition between, I wonder if there's a laser pointer.
Yes, there is. It's middle, yeah, you switch it off.
Oh, it's the middle. There you go. Thank you, yeah. So what happens here is they start off in the CC state, but with some probability, okay, because of a piece of noise, they'll transition either here, okay, because Alice's cooperate was flipped, or down here, because Bob's cooperate was flipped. So you imagine they begin by playing just rows and rows of Cs, but then some noisy event happens, okay, in this case it was Bob's noisy event, so what was meant to be a C flips to a D, and now all of a sudden Alice is mad, okay, so she defects, but actually Bob was pretty pleased because he thought, they were cooperating, and so in fact you go from the state where you're playing C, 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 you go from this state up here, because of a noise flip, over to here, C, D, and then in fact you bounce back and forth, C, D, C, D, like this, okay? And then eventually, hopefully, some bit flips again because of noise, and then you flip from bouncing around between these two states here, and you bounce back up here. If you're unlucky, you actually might get stuck down here as well. Okay? So this is just a model using the same framework, the same notational, the same notational rules to describe not Alice's mind and Bob's mind separately, but the combined states of their two minds. Okay. So that's pretty simple. In fact, we haven't done anything deep so far. All we've done is represent something I could have just said more laboriously by, say, okay, Alice is happy and Bob is happy, and so Alice's mental state is this and Bob's mental state is that. I've just represented it in a slightly more efficient way here. Okay, it looks quite pretty. Okay. Let's imagine, and this is a simple way to begin the emergence of a group mind or a group mental state. Let's imagine that I'm not interested in whether or not they're playing these particular patterns. Okay? I'm not interested in whether Bob is defecting or Alice is defecting at any point in time. What I'm interested in is whether they're doing the same thing or doing different things. Okay? Whether their payoffs are equal or unequal. I don't care if it's CC or DD, right? Those in both cases they get the same payoff. Okay? And I don't care if it's CD or DC. In that case it's a delta. They're different payoffs. Okay? So what I'm interested in is predicting a time series that's based upon this microphysics of interaction, okay, and it's just a series of zeros and deltas, okay? It's a zero if they're both cooperating or both defecting, okay? It's a delta if one of them's cooperating and one of them's defecting, okay? So now, okay, let's imagine that I want to use this representation here to predict something simpler, not the CC, DC, CD, and DD states, but just the 0 and the delta states. Okay? Well, what I do, in fact, is I can generate a simpler computational description of the system. Because I don't care about the difference between DC and CD. And I don't care about the difference between CC and DD. And so, in fact, what I get is I get a new machine that describes this time series here, and in fact it describes it perfectly. It describes it no worse than this system here. Conversely, the full description is no better than this reduced description I have here, under the assumption that all I care about is zeros and deltas. Okay? So now, up here, remember I began with mental states of Alice and mental states of Bob. Over here, I talked about their joint mental state, which was just a list, right? Now, someone's come along and said, you know what, you don't really care about the details, you care about this. Okay, zeros versus deltas. I say, no problem, I'm a smart guy, so I built this machine here, okay? But notice that these two states, this is the 0 state and this is the delta state. Notice that the delta state is no longer simply decomposable into the mental states of Alice and Bob. Okay? Delta can refer to Alice having state C and Bob having state D, or Alice having state D and Bob having state C. It's mixing the mental states of the two players. And so for that reason, we can talk about the group being in mental state delta, but not Alice or Bob being in mental state delta. Okay? So what I've done here is almost produce a computationally pragmatic account of the emergence of a mental state that's not simply a list of the mental states of the individuals. Okay? And the reason I've done that is because I have imperfect knowledge. Okay? I described it to you as saying, oh, you're only interested in zeros versus deltas. Implicitly, what I said is that you don't want to keep track of anything else. Now, why not? Well, you might not have enough intelligence, you might not have enough memory, you might not have enough data. Certainly, when we interact with society as a whole, we don't know everybody's individual mental states. Instead, we use what we call coarse-grained descriptions of our world, and those coarse-grained descriptions naturally mix together the mental states of individuals. Okay? All of a sudden, when I talk about, let's say, the state delta of the system, I'm uncertain about everybody individually, in this case. I'm completely uncertain. I don't know if it's Alice or Bob in C or D. I'm uncertain about each one individually, but what I'm hooking into are the correlations. And in fact, it's the correlations between individuals' mental states that actually lead to the group's mental state. Okay? So, for limits, for example, of not caring or imperfect knowledge, for limits of my ability to or inability to know everybody's mental state, indifference, okay? What comes up the other side is a violation of the mind-mind boundary. So the first thing we'll talk about when we look at mental states in the wild is an understanding of the system where we're going to talk about mental states, but they won't be trivially lists of everybody's mental state, or just a list, for example, of one person's mental state. So I could, for example, I could say, look, really the only thing that matters in America is what Barack Obama thinks. Now, in that sense, yes, I have coarse-grained over everybody's mental state except one man. It seems somewhat unimpressive to say that's a group-level mental state, right? If I ignore everybody except one person. What we'll see here is that it will be impossible to talk about the group without becoming uniquely uncertain about every individual. And in fact, what it will mean to talk about the group will be to talk about the ways in which an individual's mind is correlated with all the other minds in the system. Okay? So mental states in the wild now will be a story about group-level mental states that we've discovered empirically. So Wikipedia is our example system. I'm sure you all know it very well. It's a system actually that's existed for long enough now. It's in its second decade. It's over 12 years old. It's actually more than 12 years old, but our data began about 12 years ago. So actually 13 years ago. So in fact, it's a really long-running system, and in some sense, Wikipedia is over. It's something that's also interesting. Its user base is going away, in part because they finished. Wikipedia provides a remarkable example of how distributed information processing, extremely distributed information processing, appears to us. So, one introduction to this is consider two boardrooms, or imagine two boardrooms. The first boardroom is the boardroom of the Encyclopedia Britannica, which is now almost gone from the world, but of course was the premier high-status encyclopedia that middle-class families, at least in the United States, bought their children. Here's the board of the Encyclopedia Britannica. Okay, you can see some very impressive minds are including actually our Murray Gell-Mann at the Institute. Murray is of course a polymath, he knows everything because he's a physicist, he's worked with all the first principles, so he's up there. You can see some very impressive people, there are sort of lords, and there are no ladies here. Recent members, Thomas Nagel, the great philosopher, Amartya Sen, the Nobel Prize-winning economist, right? In some sense, this is the group, this is kind of a Searlean group to which you might, for example, be able to attribute a group mind through the use of shared common knowledge, joint intentionality. I imagine Searle would not have a problem analyzing that system.
A few women were added, I see.
Sorry?
A few women were
Yes. Well, this is not something that we'll be able to talk about too much, but there is, of course, and as you know, in Wikipedia. But really, what I'd like you to focus on, of course, is, this is always fun, right? What would the Wikipedia boardroom be like? Of course, there's not really a way to talk about that because the people who are essentially the board in a nonprofit legal status are not really the people who are producing or monitoring the content in the most detailed way. Okay, so if we had to come up with a boardroom from Wikipedia, it would be the list of most users with the highest number of edits, just as a proxy. Okay?
1 billion.
Right. So I know. So there's a remarkably, it takes a long time to produce this many edits, to gain this many edits. And of course, it's a fun game you can play, right? So Encyclopedia Britannica has Murray Gell-Mann, right? Wikipedia has Woohoo Kitty. There's Lord Sutherland of Houndwood, and let's see, there's Sir Amancio de Nicolau, right? So he's not actually a nobleman of Spain, I don't think. Dr. Blowfield is probably not a doctor. Okay.
Blofeld is from James Bond, the character.
Yes, I don't. Yeah, I think. Yeah, that's
Bad
the
guy.
PhD.
Yeah,
Yeah,
he's a bad guy.
yeah, he's a bad guy. Well, Wikipedia, who knows? There are many famous users. In fact, some of these users have become notorious because they've been involved in scandals, as I'm sure there will be up here as well. I don't know who on this list. Some of them, I'm sure, are very good people. So the way Wikipedia produces its encyclopedia is through an entirely different mechanism from the way Britannica does it. Okay? The ways in which it uses the minds of the people involved is very different from what you might call the political system of the Encyclopedia Britannica, right? Which is organized presumably along the ways most academic and corporate projects are organized, with a lot of understanding about what's going on, some kind of governance from below, but also a form of consensus building, people who have definitive status to talk about particular aspects of what's happening. Okay? Whereas what happens in Wikipedia, although we tend to focus on the cases in which it does look like the Encyclopedia Britannica, now we're somewhat disillusioned by the process, and it's legitimate. Okay? It's still the case that, in fact, most of what happens in a very different way than it used to happen. So, what we're going to focus on here is a computational analysis of the actions taken by users when they edit pages. So the most edited page on the English language Wikipedia, it's always fun. Would anyone like to guess?
George Bush.
Yes. Oh, you got it in one. So it is, in fact, it's actually fun to do this language by language. So, okay, what's the most edited page on the Russian language Wikipedia? Close. Stalin. Well done. And you can go down the list. So the most edited page on Brazilian Portuguese Wikipedia?
Again.
Sorry?
In Portuguese.
Football. Okay. So these pages, okay, tend to attract, language by language, and this is of course not a scholarly comment, right? It's something that you tend to notice, right? These pages tend to attract the most edited pages, the pages that attract the most participation, are not the ones that are the most intellectually challenging. Okay? They're the ones where consensus and understanding and agreement are the hardest to reach. So you should look at these pages. Look at the George Bush page. It's absolutely fascinating. Don't look at it now, pay attention. But look at the George Bush page, and it's fascinating. And what's fascinating about the George Bush page is that it's really boring. It's incredibly boring. It's as boring as a Wikipedia page written about a 14th century king, right? It's written in an incredibly dispassionate and unbelievably balanced fashion, right? It's like college students from Mars wrote this. People with no emotional investment wrote it. At least that's how it appears. But of course, it's actually written by people who have an enormous emotional investment because that's why they're there. They're there because they care about this issue passionately. And with people like Stalin and George Bush, and I suppose football, Okay? People have incredibly strong opinions about those systems, right? So here's just, if this is the polished page, right, that you could, put on the Pioneer, golden record and send off to the aliens, right? Here is the actual process by which it happens, right? This is, if you go to the talk page, which is the page that is associated with the original articles where people are supposed to hash out their differences. In fact, the first, sort of 8 inches of the talk page is not conversations, it's all these big flags that people have put up trying to encourage each other to be good. Right? There's all these different kinds of warnings. This is a controversial historical topic that may be disputed. This is a biography of a living person. Don't be mean to George Bush. Please be neutral. This is not a forum for just arguing about Bush. We actually have this goal here of producing an article that's not actually necessarily about discussing this or that policy or this or that feature of his presidency. So that incredibly neutral article is produced by a group that has the most in some sense emotional investment. So what we're going to do, because we are not qualitative researchers so much as we're mathematicians, so much as we're statisticians, so much as we're trying to get at the underlying mathematical and computational structure of the system, is we're going to take all of the actions that have happened on the George Bush page, and in fact on the top 60 most edited pages in the English language Wikipedia, and we just take the top 60 because we run out of time. We've actually done this now, we haven't published it, we've done this now for all the languages that have a sufficient number of articles that we can get good statistics on them. What we're going to do is we're going to go edit by edit. There are now, in fact, when I started working on this, there were 44,000 edits on the George Bush page. 44,000 edits. Now there's 45,000, so I keep getting more data. That's the other nice thing, is you can keep testing your hypotheses because people haven't quit. We're going to go edit by edit, and instead of taking all of the information, instead of classifying every single feature of this page, what we're going to do is we're going to classify every edit as either what's called a revert, an R action, or a non-revert, which we call C for creative or cooperative or norm-conformant. Okay? A revert action is a very simple thing that allows us to tag points of conflict. Okay? And a revert is what happens when you take something that somebody else has done and undo it. Okay? You roll back whatever addition they've made. You don't change it, you simply take it out. And of course, if it's something, if the previous action was to take something out, then you just undo that by putting it back in. Okay? So a revert in Wikipedia tracks conflict. And so this is an easy one to understand as an academic. Imagine you write a paper and you make a draft of your paper and you send it to your collaborators, send it to Francis, right? And Francis makes a bunch of edits and sends it back to you. And then you methodically reject every single edit that Francis has proposed. This would be a revert in the Wikipedia sense. And it's clear that you and Francis would at that point be in conflict of some sort. It's possible that you're not in conflict, but in general you probably are. You're certainly in what the sociologists call task conflict, and task conflict, just in case you haven't noticed, leads to what's called relational conflict. Okay. Reverts in some cases can be pro-social. It might be a good thing to do a revert. So for example, if somebody vandalizes the page, puts the phone number of their ex-girlfriend on the page, then to undo that, to revert that is pro-social. But notice that, of course, if the revert is pro-social, it's because the thing that happened right before is antisocial. It's considered norm violated. Okay? So if we track, step by step, the reverts in this page, we're tracking where conflict has erupted. So here's just an example. This is taken at random. So this is something that happens on the 13th of February, 2011, at 4:43 Universal Coordinated Time. Okay, there's a little robotic action. In fact, there's something called ClydeBot, where ClydeBot goes in and does some really minor janitorial tasks. Okay. Things get more interesting at 8:10 p.m. Okay, when a user called Ashiva 2010 shows up. And Ashiva 2010 makes an edit. He says, and in fact, he leaves a little comment so you know what his edit was. Right? His comment is, "This is a reliable source which needs to be displayed. If anyone thinks the Guardian is a biased source, or if you're conservative and you would like to object to this, please comment on my talk page." Right? So Ashiva 2010 is not somebody who's good, clearly at proactive, anticipatory conflict resolution. Right? And so in fact, what happens 20 minutes later is this user called Fat and Happy shows up. And Fat and Happy, he uses this phrase RV. It means he's reverted Ashiva 2010. All he's done, Ashiva 2010 added 453 bytes to the page. Okay? And then 20 minutes later, Fat and Happy went in and removed, and in fact it's an automatic action, you just have to click a button, and in fact undoes all 453 characters that Ashiva 2010 has added. He's reverted Ashiva 2010. Okay? Ashiva 2010 comes back 3 minutes later, okay, he does something slightly different. He calls it a revert. It's not actually a revert because he's added something else, and you can tell it's because the number of bytes is different. Okay? So 3 minutes later, Ashiva 2010 shows up, and in fact, 7 minutes after that, a user called Sox1 comes in and undoes Ashiva 2010. So Ashiva 2010 is somebody here who's involved in conflict with other users. In fact, he's involved in conflict with 2 other users. So here we would classify this little chunk of the time series, right? These, 5 edits of the 45,000 edits in the George Bush page as C, C, R, C, R. Okay? So it looks like this. Okay? And in fact, this is actually the time series for the George Bush page. This is the first edit we have a record of. Notice actually that it only takes 3 edits on the George Bush page for somebody to do a revert. Okay, so the first revert is 3 edits in, right? And then it just goes on and on. And you'll notice that there are big runs of cooperation. Okay, so I use the word cooperation advisedly, right? So really all we can say about the C's is that they're not reverts. Okay? In some sense, these could be really terrible ideas, and these R's could be like the most generous thing to do in the world. But in general, Wikipedia doesn't think that. Wikipedia tends to think, and one of the norms of the system is, that it's better to do something new, even if it's dumb, than to revert, add. That's one of the norms. It turns out to be, not held by every system. It is held by Wikipedia to be very successful. What we're going to pay attention to here are the statistics of these repeated motifs. And so I've highlighted here all the motifs where there have been 3 cooperative edits before a revert. So it begins as a revert, somebody said to something other than a revert, C, 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 and then there's a revert. Okay.
The revert is to how long into the past?
We
1, 2, 3, or
arbitrary. It can be arbitrary. So we track arbitrary. There's lots of really sort of nerdy versions of this, right? But you can track reverts in slightly different ways. It turns out not to affect the results. But it's easy just to say this revert could be taking the page all the way back up there. It could be like, I hate everything that's happened in the last year, I'm going to revert. You can undo a revert, don't worry. So we're interested in what happens, how likely it is to have a C given the number of C's you've seen before. How likely it is for a cooperative action to trigger another cooperative action, okay? So here you go. So here's the probability of one cooperative action, okay? You have a revert, then you have a C, okay? And so the probability of that, right, is the probability that you had just had the R just previously, fine, ignore that, right? And then you have, we're writing this, 1 minus P, the probability of a cooperative edit. Okay, so this is the probability of seeing an R, then a C. What's the probability of seeing an R, then 2C? So somebody does something cooperative, and then another cooperative action shows up. What's the probability of that second cooperative action? Well, an obvious idea, of course, is that they're independent. People show up, they do something, it's kind of independent of what's happened before. If that were the case, the probability of 2 C's would just be 1 minus B squared. But you might imagine some process like this, where, okay, the first C is probability of 1 minus P, okay? But then, in fact, cooperation gets easier. Okay, so instead of being 1 minus P times 1 minus P, it's 1 minus P times 1 minus P over 2, for example. Notice that P is the probability of a revert, so originally there was probability of P of a revert, now it's probability of P over 2. So we ask, and in fact, we fit this model here for arbitrary C's, and we find this really simple mathematical law, which still blows me away, and it hasn't gone away. And it turns out to be, and I'll show you some examples, it turns out to be universal across languages and universal across pages, regardless of what the pages are. There's a functional form for what we call norm contagion, how cooperative actions trigger later cooperative actions. And in fact, the way in which the probability of an antisocial action declines seems to follow a very simple power law, right? Okay, where the probability declines as 1 over I to the power alpha, where I is the number of edits you've seen, or cooperative edits you've seen so far, okay? And this describes, and this is just the probability of different lengths of cooperative runs, the probability of the function of the length of the run, okay? So if you had some kind of exponential model where cooperation was independent, you would never get these enormously long runs you'd see. So there's just the one exponential model. And even if you start adding more and more exponentials, some kind of Taylor series expansion of this, it doesn't seem to work. Instead, this very simple 3-parameter model actually ends up describing not just these kind of battles that happen here where you have short amounts of C's before a conflict, but even the emergence of these long runs of sort of highly pro-social action. So this is amazing, right? This is a run here. It's 100 steps long. Right? Everyone agreed about George Bush for 100 steps. Right? It's like, this is like remarkable. It lasted about 20 hours on Wikipedia before it died. Okay? But this is sort of the outlier event here. That event is almost impossible under any model except where you have these very long-range correlations possible. So, I've said this in words, but in fact, the actual mathematical law we find, not only does it have this functional form, but we find, in fact, that alpha, this parameter here, is about 0.5. And so what that means is the probability of defection, the probability of a revert, declines as the square root of the number of cooperative steps. So you can think about this a little bit as what we call the reverse broken windows effect. So broken windows was this famous sociological article written in the Atlantic Monthly, not known for its sociology, or not known for its academic sociology. But the broken windows effect is the story that, look, if somebody leaves litter or leaves graffiti on the side of a building, okay, that leads to more and more antisocial actions. And it was originally phrased like you have some abandoned factory, all the windows are intact, it might stay that way for months and months and months. As soon as the first window is broken in the factory, however, within a week all the windows will be broken. And the idea is that a signal of antisocial action leads to further or rapid accumulation as people learn from that single action about the ways in which that group or that society views antisocial actions. Okay? So the windows remain unbroken, one gets broken, and then all of a sudden all of them get broken. It's the broken windows effect. We find the opposite effect, which is lovely, it's the reverse broken windows. So that a small amount of cooperation makes later cooperation easier. Okay? You see a couple C's, you see people behaving well to a certain extent, and that actually decreases the probability of bad behavior. And not only that, it turns out it scales to the square root of the number of cooperative steps. Okay, the number of C's, and this is invariant over pages, so here's the sort of histogram of alpha over the 62 most edited pages. And yeah, there's some spread here, but it sits almost precisely around the 0.5 point, which is absolutely remarkable. We have no idea why. I mean, please compete with us to solve this problem. We don't know why it declines the square root. Just to give you an intuition, right, it means that, for example, the probability of a revert happening after 100 cooperative steps is about a factor of 10 lower than it was at the beginning. So it accumulates slowly, it's a square root, but it's still there, and that effect is strong enough to allow for the emergence of these long runs where people eventually stop fighting. So the alpha parameter, it turns out to be invariant across the cultures on Wikipedia, meaning the languages. Okay, so here's where English sits. So this is the other parameter, the other interesting parameter of the model, but look at the y-axis here. Here's the learning parameter. So you can see the entire English language Wikipedia, its most edited pages, sits around 0.5. Okay, and here's all languages, right? So they vary on this parameter here, but they're essentially clustering around 0.4, 0.5. Okay, they could be anywhere on this plot. They could be down at 0, which means totally uncorrelated. Cooperation is just independent. They could be up here. In fact, they cluster. Again, we don't know why. So just zoom in here. So here are all the languages. So you can see how good your ISO codes are. You can see here's French Wikipedia, and there's Dutch Wikipedia. So you can see the Dutch here, their alpha is a little lower, so their norm conformity is slightly slower than the French case. Of course, this is not about French language speakers or Dutch speakers. It's actually just about French language speakers who write on Wikipedia. There's an interesting distribution there I was quite interested by, which is, it seems that there's a sort of group up here which has higher initial cooperativity. And in fact, the most cooperative, I should have actually, the most cooperative is Esperanto Wikipedia, for obvious reasons, right? I mean, they're all, I mean, Christ, if they fight amongst themselves, how bad is the world, right? And there's actually a big cluster here of the Asian languages. I don't know what to make of it. Depending on how you notice this, there's a weird one, which is sitting right in the middle, is the Ukrainian Wikipedia, which actually I had a student at the summer school who was an administrator on the Ukrainian Wikipedia, which is a fascinating system. It's run more on the American model than the Russian model. These all, by the way, all of these language Wikipedias all invented entirely distinct social systems, meaning that they have different ways of running things. So the American Wikipedia, the English language Wikipedia is very kind of anarchist in spirit. They have some kind of monitoring. The German Wikipedia, somewhat according to national stereotype, is much more rule-bound and much more bureaucratic. The Russian Wikipedia, the Russian Wikipedia actually has voting and political parties. Political parties not meaning parties in the real world, but parties about issues on Wikipedia, which in the English language case is totally norm-violating. In the English language case, there's a norm that says there's no voting, we don't vote, let alone have political parties. So these are all totally different systems, but they're all clustering here, in this case mostly a little bit below 0.5, but roughly the same place. We learn a few things, and I'll have to skip over because I have a second thing I'd like to show you about our discovery of group mental states on a longer time scale. Okay? But we find interaction drives learning. People who interact tend to learn from each other faster. It turns out that people that interact back channel, that talk to each other, it's what we call cheap talk. It's not to affect their behavior. What we did in the second paper, having discovered this mathematical regularity, is try to build a game theoretic model, which we call asynchronous prisoner's dilemma. And the problem with Wikipedia is it's not like the usual game where you make the move simultaneously, because everyone can see what's just happened. So we imagine players coming to the page with some prior history, okay? And so in this case, the last we call this a D, because it's the model now, but this would be the revert. So somebody shows up and they have to make a new edit, and they can choose whether it's cooperate or defect, okay? So they have this choice. This is the user's choice. But the user makes that edit, and in fact, of course, what happens next is that somebody else shows up. And so depending upon whether that user defected, okay, the next user who shows up may de facto cooperate. Okay? So the system branches out, and one of these 4 paths that's taken gives different payoffs to the user. Okay, the user can benefit by defecting against the prior one, but then of course makes it more or less likely that the user who comes after will also defect. And what we find is really interesting, right? It turns out that we have to change not only the individual's beliefs, okay, but also the utility that the users get. We're unable to explain the shifting behaviors on this page simply by reference to learning. In fact, what we have to do is assume not just that our beliefs about what happens, the beliefs about the reliability of the norm, meaning whether other users are likely to cooperate or defect, it's insufficient to change that. We also have to change the force of the norm, what outcomes I desire. Okay? So we have to change not only what people think about each other, but what they want. Okay? And this turns out this is actually quite a simple thing in game theory. I don't know if it's ever been said explicitly, but it comes right out, which is that you can't have a continuous change in equilibrium, okay, if you only change the beliefs of the agents. Okay? You also have to change the utility function. Okay? And so what that means is that we have to describe this pattern here, how people edit the page and respond to each other's cooperation, not just by changing beliefs about how nice others are, but actually by changing values. It turns out that under this very simple model, if we want to explain why others cooperate, having seen cooperation, it's not just because they believe that others will be nicer, it's also because they themselves want to be nicer. And so what we have now is an idea, a set of beliefs, and a set of desires, but notice that we don't actually attribute them to any particular individual. It's a very coarse-grained description of the system. As people cooperate, we can talk about a group-level desire to cooperate and a group-level set of beliefs about what others will do. Okay? We don't actually have to attribute it to any individual. So it's in the same way that we produce this finite state model in the tit-for-tat case. We produce a model, a game-theoretic model of interaction on Wikipedia that refers only to joint desires. It has a model for a heterogeneous population. But in order to explain what we see, we only have to refer to a single parameter that governs the extent to which users wish or do not wish to conform to the norm. So, we call these micronorms the emergence of these strings of cooperative behaviors. And we call them micronorms because they're actually really fast, okay? So if, on this left edge here, this is the time scale for a single edit to register. It's about a second, right? So Wikipedia tags things to the second, okay? And Wikipedia's lasted long enough, that's in fact 10 to the -8 of the lifetime, right? Lifetime of Wikipedia is about 10 years. These unbroken runs of cooperation take about a minute to, at the most, an hour to pass, right? So they're kind of crammed down here, 10 to the -7 to 10 to the -4 of the total lifetime. And this leaves an enormous band here, what we call epic structure, right? Those cooperative runs eventually die. But what happens over long time scales? Not hours, but days and weeks and months. What's the structure of this system? And so now we go back here to this long time series, and instead of looking at these local motifs, R's and C's, turns out, by the way, if you're interested, why don't we look at strings of R's? They're really boring. Right? There are very few strings of R's that last more than a couple R's, and that's for some very interesting social norm reasons in the encyclopedia. Multiple R's are really frowned upon. Whereas the problem or the possibility of generating these long cooperative runs, that's much harder to legislate. So that's really the really interesting stuff in it. So what we've done, the thing I first talked to you about here is this, the pattern of local behaviors, little interactions. They last minutes, maybe hours. To understand what happens over weeks and months and years, we go to what we call a finite state model of the system. So in fact, what we're going to do is we're going to build, just as we built a model of the interacting tit-for-tatters, Alice and Bob, we're now going to build, and we're going to learn this, it's a very simple algorithm called the EM algorithm, we're going to learn the hidden Markov model of Wikipedia edits. Okay, so we're going to model the system as a computational process. In fact, just as Chomsky suggested, we try to model a human language. The sentences now in Wikipedia are actually these sentences that go on for years. Right? They're the sentences of C's and R's. They don't have a great, syllabary, but it's not so bad. And we're going to model some H&M. I put here, this is a wonderful diagram from Jim Crutchfield, who's one of the big figures at the Institute. This is a little diagram here of what we could call the computational hierarchy. Okay? So down here are the really simple computational structures. And up here, right at the top here, are the Turing machines, the most sophisticated computation we can imagine. Okay? And somewhere in the middle, this is this big range here, right? Birdsong falls somewhere, computer languages fall somewhere. We're going to model Wikipedia for reasons that we can get into. It's this very simple thing here. It's a Markov chain. It's a probabilistic finite state machine. It's the simplest thing that Chomsky considered. There are actually simpler things that we can talk about.
So again, just as we had some time series for the tit-for-tat case that we simplified, and in that case meant that the overall, the big computation was actually coarse-grained, and so the states here were actually coarse grainings of the mental states here. They referred, in fact, intrinsically to joint mental states, correlations between what individuals believe. We're going to do the same thing here. We're going to take these C's and R's, and we're going to model, we're going to try to build a best fit hidden Markov model. In a sense, what we're doing is, instead of generating this by analytically looking at the full machine, we're going to look at this and try to go directly from here to here. Okay, so there will be some microphysical model, right? You know, human beings, we have some reasons for behavior, and even if they're probabilistic, they are determined. Okay, they are reliable patterns, hopefully. They might be incredibly sophisticated. So you should imagine going from here to here as going from the joint mental state of the tens of thousands of people, right? So you know, think about how complicated you are, right? And now, you know, take the tensor product of that, you know, 100,000 times, right? So that's how large that machine would be. What we're going to do is we're going to try and model it directly from the time series. And here's what it looks like. Okay, here's the finite state machine for edits on the George W. Bush page where all we care about, okay, where all we care about is whether people cooperate or defect. You can see things right away. Don't worry about the numbers, just the label states if you want to talk about the state. But if a state's labeled D, it means it's a generally defecting state, people revert. If it's labeled C, it's generally a cooperative state, they don't revert, do something else. And there's occasionally, here's a CD state, this is where the behavior is much more stochastic. One of the things you can see right away, it's obvious visually, right, is that in fact this thing falls into two modules practically. There are very few transitions between these two modules, but actually the system will stay here, bounce around here. And so you can think of this as what we call the garden of forking paths, right? So you might start in this state here, and you might bounce up there, and there at each time step, right? So in this case, probably you see something, maybe a C or a D, then you definitely see a D, then you definitely see a C, then you definitely see a D. You're bouncing around, you see a C. But maybe you took a slightly different path, you went up there, you went down here. The paths that this system takes, okay, through its computational states, is the history of the encyclopedia. And this is just telling you the overall laws that govern the transitions between them. Right? It's visually obvious. In fact, it's possible for the system. We don't show the arrows because they're so low probability. Even though we only have one arrow from here to here and none going the other way, there are actually very rare transitions to go to the other module. But practically speaking, what we have is two subsystems. And we can talk about the dwell time, how long you get stuck in one state versus the other. And you can get this exactly from what's called, it's the second eigenvalue of the transition matrix, right? But you can just turn it into a tau. Tau is the number of time steps you're stuck in one versus the other. In the case of the George Bush page, you're stuck basically in one of these substates for about 1,500 edits, 1,500 edits. That's how long you stay resident in one of these versus the other. Okay. The dwell time varies, so in the Barack Obama page, it's actually much lower, it's 53 steps. You can see the modules are there, but they're pretty confused. In fact, there are some other pages where the dwell time is enormous. It's almost as long as the page itself. The page basically started in one module and went to the other. It happened only once. I'll tell you why. In this case, it happened. It's very interesting. So the dwell time is a histogram. Okay, the dashed line. Yes, sir?
What was the difference between the dotted arrows and the...
Oh, these are strengths of transition. So the solid lines are transitions of order 10%. The dashed lines order 1%. The dotted lines of order 0.1%. And then, but there are even rarer transitions that we don't show. Otherwise, just be a big hairball. You couldn't see them. So, just to give you a guide, so you can see, for example, that here, this is the dotted line. So in fact, it's even very rare to go from here. So you can look at the dwell time. The dash line it's just a null model just to show this is a real thing. But you can see most of the dwell times, most of the time you get stuck in one side versus the other, one module versus the other. There's hundreds of time steps, right? Many hundreds of edits. We can actually track the passage that the group as a whole takes through this system using something called perturbing path reconstruction. So we can actually find the maximum likelihood path the system took over time. So we can say, look, what was happening? Where were you at, January 1st, 2002? Which of these states were you in? And we can actually approximate that as best we can. What we find, for example, in the George Bush page is that there's only about 10 mode switches between these two states over the entire course of the page's history. Over 10 years, the system switches back just about 10 times. And the reason that's very interesting is that these two modules, not only do they represent different local patterns, different motifs of interaction, but one of them, in all cases, is what we call a high cooperative state. It's mostly C's. And in the other case, it's warm. It's a low cooperative state. It's a high conflict state. And we can track, and this is just the example of the George Bush page here, blue is high cooperative and red is low cooperative, and this is just the fraction of cooperation over time. Okay, so starting in just sort of late 2001, you can see the system starts out in the cooperative state and then sort of jigs around and pow, it hits this, goes into this module for a long time, goes pow, back up. She switches a little bit back and forth, right, over time. Okay? It's important to note, right, that it's not just the level of cooperation. So consider this line here, which is about 70% cooperation. If you're enjoying 70% cooperation, you might be in one of these two states. What distinguishes you is the local patterns. What happens when one person defects and the other person cooperates? So these are actually, they're incredibly distinct on the microstate level. They happen to be associated with high levels and low levels of conflict respectively. So in some sense, this is War and Peace Online. This is the underlying computational structure. Highly modular. Highly modular. This is, of course, how things unfold second by second, but as we all know, internet time is very different. So look at this red patch here. It's a pretty short space, but if we go edit by edit, we see, in fact, it's an enormous range of the actual total edits in the encyclopedia. Okay? What this means, in fact, is when you're in the high conflict module, time accelerates, conflict acceleration. And in fact, edits happen about 10 times faster than they do in the low conflict state. So I have a little bit more time, and I'll tell you the story. In fact, this gets to something that Marta and Francis and I were talking about on the way over here. Right? What causes this switch? You get stuck in one module for a long time. What kicks you out to the other one? In the models we have, right, it's the internal logic of the process, but that's because we don't include the environment as any kind of, we don't model the environment simultaneously. But what we can do, because of Viterbi path reconstruction, is we can actually pinpoint the exact second that the system switches modes, when it goes from high conflict to low or low conflict to high. It's probabilistic, we don't quite sure. I mean, the algorithm says it happened right here, but we know that's just a fuzzy picture. Okay, might flip back and forth. But we can pinpoint reasonably well, within to about 12 hours, exactly where that transition happened. So what are the causes of mode switching, right? Here's just a passage. This is on the George Bush page again, because there's so much data, it's the best fits we get. But we find, for example, that mode switches occasionally occur when an administrator comes in and does one of these top-down actions. And what they can do is lock the page. They say, look, enough is enough. I'm angry for some reason. And only trusted users are allowed to edit. Or in fact, I don't even trust the trusted users. Only people like me can edit. So they can lock down the page. Or conversely, they can liberate the page and say, okay, enough. It's a free encyclopedia, right? So this is top-down control. Does top-down control work, right? When an administrator locks the page, do people actually flip to the low conflict state? The answer is sometimes. Okay, so we have in our data 712 protection events. This is when an administrator comes in and does this top-down action, tries to lock the system down. We have 712 top-down actions. 79 are associated with mode shifts, right? So essentially, only 11% of the protections had an effect. It's about 1 in 10 chance that when an admin comes in and locks the page, they're able to kick it into the positive. In fact, we actually even track it when it kicks into the negative state as well. Sometimes it does. But in fact, mode, this external action, which is totally radical, it completely changes the audience of the page. From anyone can edit to Wikipedia nerds can edit to Wikipedia super nerds can edit. And in fact, all those changes, right, they're only about 10% effective, right? We say that they're ineffective. And conversely, they can only explain about 10% of the mode switching, right? So they're not particularly explanatory. The next thing we wonder is, okay, so look, it's not one person, it's not this single external flip, right? That's not what distinguishing the states in one mode from the other, right? In that case, we sort of be like Alice's state is the one that matters. Then we wonder, okay, look, is it particular users, right? Maybe it's a small group of people, and when they show up, they kick the state here, or they kick it back. It could be different groups at different times, but isn't the case, for example, that somebody particularly antisocial would show up and start a war, start a fight, right? And there are a couple associations. This is one, actually, this is the first mode switching event we see on the George Bush page in September 2004. And when you go look at what's happening, you see a bunch of people show up. A guy called Very Verily, a guy called Kevin Boss, Gazornenplatz, Guanaco, right? It's just the standard internet, synonymity, right? And in fact, they show up and they get into such a huge fight over how to represent George Bush, and I have, it's amusing. I'm not upset by it, or it's not something. It's amusing to see this happen. But in fact, it gets so bad that they have this huge sort of Wikipedia court case. And I think they partly invent the institution of these sort of administrative reviews that involve all of these people, Very Verily, Zornenplatz, Karen Boss. In fact, these users keep showing up over and over again. So this is a transition, a mode shift, a mode switch that seems to potentially be associated with a couple individuals, one or two maybe showing up, who have trouble getting along, right? So in fact, there's an enormous amount of text devoted to it. And this court case here shows up, in October. The mode switch happens in September. Interestingly, it turns out that even though you can find these associations and tell a story, there's really no signal. It's a null signal. Okay, so maybe it's real, but we have no statistical evidence that these are anything other than post hoc stories. Okay, there is no evidence that particular users can kick the system. Okay, it's either effective or explanatory. So the final thing to consider as a sort of deflationary account of the mode switching events, an account that would say that, look, the difference between these states and those states is not some really interesting group mental property, some collective state, or not some simple external shock, but something more sophisticated. The last thing we consider was the possibility of outside events, right? So, people were having this discussion, all of a sudden politics intrudes from the outside. Something happens related to the subject of the article, maybe that draws in new people, or maybe it somehow triggers an argument. So we can model this. We go and we use the APIs of various newspapers. We have the New York Times and the Guardian, and we're trying to get more. But this is how the news cycle looks for Barack Obama. So we can consider the spike ratio. So take any 4-day period, right? The rate of articles, in this case on Barack Obama, and consider the ratio of that rate to the rate over the previous month. Okay? In general, the ratio should be about 1. There'll be some fluctuations around it, right? So, sometimes, there's a sort of slow news day for Obama, the ratio's low. Sometimes it's kind of exciting. Occasionally you have these rare sort of peak events out here, right, where the coverage is 8 or 10 times more than it usually is, right? So this would be an extreme event like an election, right? So we look, is there a signal of mode switching associated with an extreme news event in the real world that we get from the newspapers? And here's a potential example. This is a positive mode switch. So this is a switch somewhere in these edits here. I can't quite see. Somewhere in these edits is where we detect from vectorial path reconstruction a switch of modes. And actually it's a nice one. It's a switch from the high conflict to the low conflict state. And it's interesting because it exactly coincides with Obama first announcing that he's considering running for president. And in fact, if you look at what's happening here, you can see that maybe this is, you can see that there's some kind of like low conflict stuff going on because all these people are showing up and they're so happy. And they're basically collaborating to sort of talk about how excited they are about Barack Obama and put all this sort of, not necessarily positive information, but they're collaboratively trying to do something to represent Obama better. They're not arguing. They're mostly people who are really pleased and in a really good mood. And it's kind of fun to read, like everybody's, even when they revert each other, they're really nice about it. Like, I gotta revert you because this is already somewhere else. Yes?
They would only become disappointed years later.
Yes, exactly. So, sadly, this is one example of positive mode switch. Here's another one. This is on the Argentina page. It's a radical spike in news associated with Argentina playing some kind of football match, right? If you actually look in the edit history, it has nothing to do with football. So this is just a coincidence. And in fact, in general, pages are largely immune to mode switch to news associations. And again, you have to be careful, right? So there is a spike in news coverage for Argentina that occurs roughly coincident with the mode switch. But the news spike is in football. The mode switch here appears to be some sort of kind of weird debate about how you should represent the Jewish population in Argentina. So the claim we make here is, okay, we have practically null results. There's some evidence that administration move matter, but otherwise there's not much. Okay? And so the claim here is that we have some notion of a delocalized mind, right? The difference between these states here and these states here is not a simple exogenous event. It's not a mental state associated with 1, maybe 2 or 3 people, right? Somehow, what distinguishes these two are facts about large clumps of individuals. These are really sort of 0 and delta states we had in the original Tit-for-tat case. So what I've given you here is a story, sort of 2 sources of group minds, right? One on the second by second, minute by minute level, one on the decade level, practically, on the months and years level, right? We have this remarkable reverse broken windows result. Alpha is 0.5 across all languages, across all pages, roughly, okay, within error. And we can give a parsimonious explanation to this incredibly simple mathematical law by referring to group common knowledge about Nash equilibrium, and by referring to properties of the system cooperativity that refer to no individual in particular. That's all we need to do. We could go more fine-grained if you like, but we're able to produce a description about the thing we care about, which is how much people are, norm-conforming within the encyclopedia. We can produce that description by referring only to a mood of the system as a whole. Okay, that's predictive. And when that's predictive, Okay? If we're tired enough, if we're limited enough as predictive beings, then we will simply go ahead and do it. And that's, in some sense, a mathematical story of what we do all the time. The crowd turns ugly. Everyone's mad on the train this morning. And the other thing we do is this much longer timescale story, which is about computational states that don't reduce to individual actions. So you guys have been fantastic. I'm going to skip the really nerdy part, which is great. We can talk about it as you please. It's really good. Really, God, look at this.
That's why we skipped it.
Yeah, no, exactly. So I will just, I'll just tell you briefly these. There are 4 papers, and you guys will have the slides, of course. 2 papers on the phenomenology of these cooperative runs, and on a game theoretic model that also talks a little bit philosophically about what it would mean to attribute group mental states. Okay. Metaphysically, who knows? This is a pragmatic account. If you want to describe what happens on the encyclopedia, and you don't have the power to think about everybody all at once, your mind can't grasp 100,000 minds. This is true for most of us, maybe not Hegel, but for most of us, you can't do this. So when you actually want to describe, when you want to make scientific descriptions, predictive, explanatory descriptions, you will tend naturally to talk about group mental states. And in fact, they're scientifically useful, meaning that they give you predictive leverage on what happens, and they also may even give you explanatory leverage, right? So notice when we look, for example, at the mode switching events, right? We can zoom in and say, look, this is a positive to a negative mode switch. What causes it? Okay. Positive and negative here, they are properties of the state of the system that naturally involve correlation between the underlying mental states. So there's that, and then there are also some more methodological articles that we've done. One with Adair Wolpert, Josh Grochow, and Eric Libby, which is on a large-scale framework for producing coarse-grained descriptions, which is underlying a lot of the justification here. And this is a paper about coarse-graining the finite state machines, which is something that we began with, right? So we began with that sort of complicated transition matrix for the tit-for-tat players, and we talked about how to crunch down the states, how to coarse-grain those states in reliable ways. This is something that we've dealt with a little bit in a paper back in 2012. So I will put up a picture of the group we have in Indiana. It's a great group of people. We just had a great dinner, and so I had to get on the plane right after a really fantastic dinner, so you can imagine how much fun that was. But it's a pleasure to be here. Thank you very much for coming to the talk, and I think we have plenty of time for questions, so thank you very much.
Thank you very much.